Welcome to today's paper reading. Today's paper is titled, An Image is Worth 1/2 Tokens After Layer 2, Plug-and-Play Acceleration for VLLM Inference. This paper was published on AR14 by Liang, Chen and colleagues from Peking University and Alibaba Group. In this study, the authors identify inefficiencies in the attention mechanisms of large vision language models, LVLMs, particularly in models like LVLMs 1.5, QwenVL-Chat and Video-LLaVA. They find that the computation of attention over visual tokens in the deep layers of these models is highly inefficient, suggesting a need for a more sparse approach compared to textual data processing. To address this, the authors introduce FastV, a method designed to optimize computational efficiency by learning adaptive attention patterns in early layers and pruning visual tokens in subsequent layers. Evaluations show that FastV can reduce computational costs by up to 45% without compromising performance on various image and video understanding tasks. The trade-off between computational efficiency and performance is customizable and Pareto efficient, allowing for significant reductions in flops while maintaining superior performance. Figure 1 illustrates the trade-off between computational efficiency and performance for FastV. The x-axis represents the theoretical reduction in floating-point operations, flops, under various FastV configurations, while the y-axis indicates performance across different settings, measured by average scores on benchmarks including NoCaps, Flickr 30K, AOKVQA, and MMU. The graph demonstrates that FastV can achieve a 45% reduction in flops without compromising performance. This trade-off is highly customizable, allowing for adjustments to achieve different levels of computational efficiency. Additionally, the results show that FastV is Pareto efficient, meaning it can compress the flops of a larger model to match or outperform a smaller model in terms of performance, making it practical for deployment in edge devices and commercial models. Large vision language models, LVLMs, are transforming how we interact with AI systems by combining vision and language capabilities. These models are used in a variety of applications, from image description to real-world decision-making. However, current LVLMs often rely on a sequential visual representation, where images are converted into tokens, leading to increased computational complexity and costs. This paper identifies an inefficient processing method where image tokens receive significantly lower attention scores compared to text tokens, particularly in deeper layers of the model. This imbalance raises questions about the optimal use of visual information in LVLMs. The development of large vision language models has seen the use of a visual prompt generator to transform visual embeddings into language model prompts, leading to a significant increase in required tokens, especially for high-resolution images. In the realm of inference optimization for large language models, methods have been developed to optimize memory consumption and prune redundant attention computations, though these are primarily designed for text-only models. Prior to the era of large vision language models, studies focused on improving the efficiency of vision language models through token reduction techniques, with FastV being the first to explore this for large models, demonstrating its effectiveness in video QA and comprehensive benchmarks. Figure 2 illustrates the classic network architecture of a large vision language model, LVLM. The process begins with image tokens and various types of text tokens being fed into the large language model, LLM, as input. The LLM then generates output tokens in an autoregressive manner, meaning each new token is generated based on the input tokens and all previously generated output tokens. This architecture is fundamental to how LVLMs process and generate responses to multimodal inputs. In vision language large models, VLLMs, visual tokens, despite being a significant portion of the input, receive significantly less attention compared to system prompts. This attention imbalance is more pronounced in deeper layers of the model. In shallow layers, attention allocation is relatively balanced, but in deep layers, the majority of attention is directed towards system prompts. Specifically, system prompts have an attention efficiency 472 times higher than that of image tokens in deep layers, accounting for 85% of the total attention scores. This imbalance suggests that while image tokens are numerous, they are not effectively utilized by the model. Figure 3 illustrates the inefficient visual attention phenomena in large vision language models, LVLMs. On the left, it shows the relative position and average number of different types of input tokens, where image tokens make up 64% of the total. The middle and right parts display the average attention allocation, lambda, and attention efficiency, epsilon, in shallow and deep layers. Notably, image tokens receive significantly less attention compared to their proportion in the deep layers, while the system prompt has an attention efficiency 472 times higher in deep layers. Figure 4 illustrates the attention maps during the decoding process of a model response for LVLMs 1.5-7b. In the bottom layer, attention is distributed relatively smoothly across different types of tokens. However, in the deep layers, the attention scores are primarily aggregated to the system prompt, instruction, and output tokens, with attention over image tokens being rather sparse. This pattern highlights the shift in focus from a balanced attention distribution in the shallow layers to a concentrated focus on specific token types in the deeper layers of the model's decoding process. Figure 5 illustrates the FastV process, which involves transforming image or video inputs into visual tokens using a pre-trained image encoder like QwenVL-Chat. These tokens are then processed by a large language model, LLM, decoder. FastV dynamically prunes a specified percentage, R%, of image tokens after a certain layer, K, in the forward process. This pruning significantly reduces the number of floating point operations, flops, without compromising the correctness of the outputs. The correct facts in the outputs are highlighted in green, and it is noted that the first three outputs remain completely identical despite the pruning. This method effectively balances computational efficiency with output accuracy. FastV is designed to significantly reduce the inference costs of large vision language models, LVLMs, while preserving their performance. This solution is easily adaptable to various LVLMs and vision language tasks without requiring additional model training. The core of FastV involves a dynamic pruning mechanism for image tokens, which includes a ranking function and two parameters, the filtering layer K and the filtering ratio R%. This approach allows for a theoretical estimation of flops reduction, which is visualized in a 3D graph. Additionally, FastV is compared to alternative methods of reducing visual tokens, demonstrating its efficiency in computation reduction during the inference stage. Figure 6 presents a heat map illustrating the theoretical flops reduction ratio as influenced by the parameters K and R in the FastV model. The heat map uses color to represent different levels of reduction ratio, where K denotes the layer at which token pruning begins, and R indicates the percentage of tokens reduced. This visualization aids in understanding how varying these parameters affects the computational efficiency of the model. Table 1 illustrates the balance between performance and computation for FastV under various configurations. The table shows the impact of different K, filtering layer, and R, filtering ratio, values on flops, floating point operations, reduction in performance metrics across multiple models. Key configurations include K values of 2, 3, 5, and 0, and R values of 90%, 75%, and 50%. The flops reduction ratios range from 19% to 100%, indicating significant computational savings while maintaining or improving performance. The highest scores for each model are highlighted in red, with the second highest in blue, providing a clear visual comparison of the best performing settings. Table 2 presents the results of experiments involving more models and benchmarks. The table highlights the performance of various models, including LVLMs 1.5-13b and InstructBlip Vicuna-13b, when combined with FastV under different configurations, K for filtering layer, R for filtering ratio. Key metrics such as AI2 diagram, SciQIMG, Seedbench, MMVet, and MME are reported. For instance, LVLMs 1.5-13b with FastV, K equals 2, R equals 50%, achieves a score of 59.45 on AI2 diagram, while InstructBlip Vicuna-13b with FastV, K equals 5, R equals 50%, scores 44.39 on SciQIMG. These results underscore the impact of FastV configurations on model performance across a range of benchmarks. Table 3 presents the fine-grained results of the LVLMs 1.5-13b model enhanced with FastV, k equals 2, r equals 50%, on the NME benchmark. The table breaks down performance into specific tasks such as exist, count, position, color, OCR, poster, celeb, scene, landmark, art, number, text, and code. Each task is scored individually, and the total score is also provided for comparison. This detailed analysis helps in understanding the model's strengths and areas for improvement across different aspects of multimodal evaluation. The evaluation of FastV on large vision language models, LVLMs, was conducted across a variety of tasks including image captioning, visual question answering, VQA, multimodal reasoning, and video question answering, QA. The models tested included LVLMs 1.5-7b, 13b, and QwenVL for image understanding tasks, with Video-LLaVA as the baseline for video understanding tasks. The main results show that FastV can maintain or even improve performance while significantly reducing the number of floating-point operations, flops. For instance, a 13b model with FastV can perform inference as quickly as a 7b model without FastV, while maintaining superior performance. This efficiency is particularly notable in video QA tasks, where FastV not only reduces computational load but also enhances task performance. Table 4 presents a detailed comparison of the real inference budget between FastV and vanilla decoding methods. The analysis is conducted on the AOKVQE dataset, focusing on the inference latency and GPU memory usage. The table highlights that an LVLMs 1.5-13b model with FastV can achieve inference speeds comparable to an LVLMs 1.5-7b model, while maintaining superior performance scores. This demonstrates the efficiency and effectiveness of FastV in reducing inference time and resource consumption without compromising on model performance. Table 5 presents fine-grained results on PCA bench and OCR VQA, focusing on the perception, P, cognition, C, and action, A, scores. The genuine PCA, GPCA, score indicates the model's ability to correctly perform all three tasks for a single test example. These scores are averaged across three domains: auto-driving, domestic robot, and open-world game. The table highlights the performance of different models, including LVLMs 1.5-7b and LVLMs 1.5-13b with various FastV settings, showing their respective flops and scores in these tasks. Table 6 presents the GPT evaluation results on various video question answering tasks, including TGIF, MSRVTT, and MSVD. The table highlights that the Video-LLaVA model, when optimized with FastV, k equals 2, r equals 50%, significantly reduces the computational cost, flops, to 52.3% while maintaining or improving accuracy. Notably, the TGIF task demonstrates a 0.03 increase in accuracy with FastV, indicating that the optimization strategy effectively handles redundancy in video data. The average scores across tasks also show a slight improvement, suggesting that FastV not only reduces computational load but also enhances overall performance in video understanding tasks. Table 7 presents the results of ablation studies conducted to understand the impact of different parameters and strategies on the performance of the LVLMs 1.5-7b model. The table includes scores for various configurations of the model, such as training with reduced image tokens, using FastV with different parameters, and pruning strategies. Scores labeled as failed indicate instances where the model could not generate valid results for evaluation. The study highlights the balance between computational cost and performance, showing how different configurations affect the model's ability to handle tasks like OCR VQA and multimodal reasoning. Key findings include the performance degradation when reducing input resolution during training and the effectiveness of FastV in reducing image tokens without compromising performance. Figure 7 presents an ablation study focusing on the filtering layer K and filtering ratio R within the FastV framework. This study is conducted using the LVLMs 1.5-13b model on the OCR VQA task. The key findings indicate that when K is small, reducing R can enhance performance with a smaller reduction in flops. Conversely, when K is large, altering R has a minimal effect on overall performance. This suggests a high redundancy in image tokens within deep layers, emphasizing the need for careful parameter adjustment to balance performance and computational efficiency. In this paper, the authors introduce FastV, a plug-and-play method designed to optimize inference costs for large vision language models, LVLMs. The key insight behind FastV is the observation of inefficient attention computation over visual tokens in the deep layers of popular LVLMs, despite these tokens comprising a large portion of the input. FastV addresses this issue by pruning unnecessary visual tokens based on attention score rankings, leading to a significant reduction in inference costs without compromising model performance. Thank you for watching.